Formulae set 2 Formulae set 2 of the chapter circular motion Number 1 topic is motion of a body in a vertical circular plane. Motion of a body in a vertical circular path. So this is the vertical circular path, and a body of mass m is tied to one end of a string, and the string is whirled in this vertical plane. So at the point B, we have the body of mass m. M is the mass of the body at the point B in this vertical circular plane, and this body of mass m has a tendency to move with tangential velocity Vt in this direction. V2 is the tangential velocity at the lowest point B. The weight of the body mg is the weight of the body which acts vertically downwards. O is the point of this vertical circular path, and OB is the string of length r. And on this body at the lowest point B in this vertical circular path, on this body T2 is the tension acting in the string OB. OB is the string and on which T2 tension is acting. A centripetal force Fc2 is acted on the body B so that it will rotate. It will rotate in this vertical circular path anti-clockwise. When the body reaches at the highest point E is the highest point of this vertical circular path, and the body has a tangential velocity v1 at the highest point A. v1 is the tangential velocity. The weight of the body at the point A acts downwards. mg is the weight of the body at the highest point A, which acts downwards. Tension acting in the string is T1. T1 is the tension. T1 is the tension acting in the string at the highest point. mg is the weight and T1 is the tension. All are acting from the center of gravity of the body. And centripetal force, the external force, which is the centripetal force which will be applied on this body at the highest point in vertically downward direction. Fc1 is the centripetal force which is acted on the body at the highest point. This is the vertical circular path in which circular path or plane in which the string OB is rotated and a body of mass m is tied to one of the end of the string. R is the length of the string and also radius of the vertical circular path. At the highest point A of this vertical circular path, highest point A, it should be vertical circular path, not vertical circular plane, and at the highest point A, centripetal force Fc1 is mg plus T1. So now centripetal force has the expression mv1 square by r equal mg plus T1. mv1 square by r equal mg plus T1. So this is the expression of centripetal force at the highest point. If T1 is equal to 0, that means tension acting in the string at the highest point A is 0. In that case, tangential velocity of the body at the highest point will be v1, which is root over rg. v1 equal root over rg, where r is the length of the string or radius of the vertical circular path. v1 equal root over rg, which is the velocity of the body. velocity of the body revolving in a vertical circular path or plane. V1 equal root over rg, which is the velocity of the body which is revolving in vertical circular path at the highest point A. Provided tension acting in the string at the highest point is 0, that is minimum, T1 equal to 0, then V1 equal root over rg. So at the highest point, Fc1 is the centripetal force, which is sum of mg and T1, sum of weight of the body and tension acting in the string, is equal to the centripetal force Fc1 at the highest point A. At the lowest point B of this vertical circular path, at the lowest point B in this vertical circular path or circular plane, Fc2 equal, that is the centripetal force Fc2 equal T2 minus mg. T2 is the tension acting in the string at the lowest point, or comma mv2 square by r is equal to T2 minus mg. mv2 square by r equal to T2 minus mg, which is at the lowest point B of the vertical circular path. According to the principle of conservation of energy between the 2 points B and E, according to the principle of conservation of energy, or this principle can be considered between the 2 points B and A, we get sum of kinetic energy and potential energy remains constant. That means EKB plus EPB. That means sum of kinetic energy and potential energy at the lowest point B will be equal to EKA plus EPA. EKA is kinetic energy at the highest point, or half mv2 square plus mg into 0 equal half mv1 square plus mg into 2r. Here height of the body at the point B with respect to the point B is 0. That's why potential energy at the point B is 0. At B, height h2 is 0. That's why potential energy at the point B, EPB, is mgh2 equal mg into 0. At the highest point A, height h is 2r, that is the twice of radius diameter or twice of length of the string. Potential energy is EPA equal mgh1 equal mg into 2r. From this we can prove that V2 equal root over 5gr. V2 equal root over 5gr. That is the velocity of the body at the lowest point B. Velocity of the body which is rotated or whirled in a vertical circular path at the lowest point B. And we can prove that and also at the lowest point tension T2 is mv2 square by r plus mg. Therefore T2 equals 6 mg, 6 times of weight of the body. T2 equals 6 mg, which is the tension acting in the string at the lowest point B. Tension acting in the string at the lowest point B. Now additional information. At the lowest point B, tension T2 is 6 mg and tangential velocity V2 equal root over 5gr. At the highest point A, tension T1 is 0 and tangential velocity V1 is root over gr. So here we can memorize 6501. Tension T2 is 6 mg, that's why it is 6, and 5 for tangential velocity V2 equal to root over 5gr, and 0 means tension acting in the string at the highest point T1 is 0, and 1 means tangential velocity at the highest point A is V1 equal root over GR. So memorize 6501. Number 2 topic is velocity of a body moving in a vertical circular path or plane, and the tension acting in the string which becomes parallel, or when the string becomes parallel to the horizontal direction. This is a vertical circular path, and the string is parallel to the horizontal, and we have a body of mass m which is tied to one end of the string, and the string is rotated in vertical circular plane, and the string comes at the point C. R is the length of the string or radius of the vertical circular path. The string is rotated in anti-clockwise direction. At the point C, the body has a tangential velocity V3. The body has a tangential velocity V3 at the point C, at which string becomes parallel to the horizontal. At C, weight of the body, that is mg, acts vertically downwards, and a tension T3 acts in the string towards left along CO. Tension T3 acts radially inwards along CO, and this tension T3 provides the necessary centripetal force Fc3 at the point C. We have to find the expression of T3 and V3. Let the string be parallel to the horizontal direction at the point C. String be parallel to the horizontal at C. And also we can draw another radius, and when the body was at the point at the lowest point B is the lowest point, and m is the mass of the body at the point B, and at the point B the body has a tendency to move along the tangent with velocity V2. V2 is the tangential velocity at the lowest point B. Weight of the body mg acts vertically downwards at the point B. Now we have to find the expression of V3 and T3. At the point B, tension T2 acts in the string upwards, and Fc2 is the centripetal force acting on the body at the lowest point B. Using the principle of conservation of energy between the 2 points C and B, we get, using the principle of conservation of energy between the 2 points C and B, we get half m V3 square plus mg into R, sum of kinetic energy and potential energy, equal half m V2 square plus mg into 0. 0 is the height of the body at the point B with respect to the point B. Now V2 equal root over 5gr in the diagram. So we can prove that V3 equal root over 3gr. V3 equal root over 3gr. V3 equal root over 3gr, which is the velocity of the body when the string comes parallel to the horizontal. Velocity of the body when the string becomes parallel to the horizontal direction. Also, T3, tension T3 is only equal to Fc3, is equal Therefore, T3 equal 3 mg, putting the expression of V3. T3 equal 3 mg, which is the tension acting in the string, which comes parallel to the horizontal direction. Tension acting in the string. T3 equal Fc3, where Fc3 equal mv3 square by r and V3 equal root over 3gr. From that we can prove that T3 equal 3 mg, which is the tension acting in the string. Now T3 is the tension which supplies necessary centripetal force Fc. Component of mg in horizontal direction is mg cos 90 degree. That's why T3 equal Fc3. Number 4 topic is tension acting in the string. Tension acting in the string. To which a body is tied. To which a body is tied and rotated in a vertical circular path. Rotated in a vertical circular path or plane. In a general position. In a general position. In diagram, the string comes at this general position, in which the string makes an angle theta with the vertical. O is the center of this vertical circular plane or circular path, and P is the point, or P is the point at which the string makes an angle theta with the vertical. Mg is the weight of the body which acts vertically downwards. Mg is the weight which acts vertically downwards. At the point P, the body has a tangential velocity v. At the point P, the body has a tangential velocity v. And the string makes an angle theta. The string OP of length r makes an angle theta with the vertical. Weight of the body mg is resolved into a rectangular component. Mg cos theta. This angle will be again theta, and the rectangular component of the weight mg is mg cos theta, which acts radially outwards. Mg cos theta is the rectangular component of weight of the, and tension T acts towards the center O. T is the tension which acts along the string radially inwards, and the centripetal force acting on the body at the point P is Fc. Fc is the centripetal force. Centripetal force. And m is the mass of the body. At the point P means at the point P in general position, centripetal force Fc is equal to T minus mg cos theta, or T equal Fc minus mg, Fc plus mg cos theta. Therefore T equal mv square by r plus mg cos theta. T equal mv square by r plus mg cos theta. This is the tension acting in the string in general position, in which the string makes an angle theta with the vertical. Tension acting in the string. Tension acting in the string when the string is in general position. That means the string makes an angle theta with the vertical. T equal mv square by r plus mg cos theta. And this is the highest point. When the body moves to the highest point A, it has a tangential velocity v1. The body has the tangential velocity v1. At the highest point A, mg is the weight of the body and tension is T1. T1 is the tension acting on in the string. Weight of the body is mg centripetal force will be greater than T1 and mg, that is Fc1. Additional information that at the point A, that means at the highest point A, theta equal 180 degree angle subtended by the string OA with the vertical is 180 degree, theta equal to 180 degree, then T1 equal mv1 square by r plus mg cos theta. Putting the expression of theta, then that is 180 degree mv1 square by r minus mg, because cos 180 degree is minus 1. T1 equal mv1 square by r minus mg, that is the tension acting in the string. That is the tension acting in the string. At the highest point A. So we can find the expression of tension acting in the string at the highest point or lowest point by using the general formula. Next topic, or number 4 topic, is what? Conical pendulum. Conical pendulum, and we have to find the expression of time period of this conical pendulum. This is the horizontal circular orbit. This is the horizontal circular orbit in which a body will be rotated in vertical direction, and a body is suspended by using a string. This is a body of mass m which is at the point P. O is the center of the horizontal circular orbit. P is the point at which the body is placed, and this body is tied to one end of the string, and the string is fixed to a fixed end, fixed to a horizontal ceiling, and mg is the weight of the body which acts downwards. B is the fixed point to which the string is connected, and the string is rotated in this horizontal circular orbit anti-clockwise according to the diagram. R is the radius of the horizontal circular orbit. We can T is the tension acting in the string which acts along PB. T is the tension which acts along PB in the string, and we can resolve this tension T into 2 rectangular components. Now the string makes an angle theta. The string PB makes an angle theta with the vertical direction OB. Theta is the angle subtended by the string with the vertical, and length of the string is L. We can denote the length of the string. L is the length of the string. L is the length of the string. Now 2 rectangular components of the tension T is T cos theta which acts vertically upwards, and T sin theta which acts radially inwards in horizontal plane. And this rectangular component T sin theta supplies the necessary centripetal force Fc. Magnitude of them will be same. Fc is the centripetal force which acts radially inwards and supplied by the rectangular component T sin theta. As T sin theta supplies necessary centripetal force Fc, that's why T sin theta equal T1 sin theta is equal Fc, and Fc equal mv square by r. Here the tension T can be denoted by T1, not T actually. So T1 cos theta is equal mg, and T1 is the tension. In the diagram we can change the tension T, that is by T1. T1 is the tension acting in the string. T1 is the tension which is resolved into 2 components, T1 cos theta and T2 cos theta. And here from that we can prove that the time period of oscillation of the body is T, which is 2 pi by omega. T1 is the tension and T is the time period. So we get the expression of time period T as 2 pi root over L by G. T equal 2 pi root over L cos theta divided by G. This is the time period of oscillation of the body for the conical pendulum, time period of revolution, not oscillation, time period of revolution of conical pendulum, time period of revolution of conical pendulum, where L is the length of the string. Now in triangle POB, sin theta equal R by L, radius by length of the string, where L is the length of the string. Length of the string. Time period is T and T1 is the tension. Number 5 topic is the maximum height from which the motorcyclist in a globe of death must start in order to go round a globe successfully. Initially, the motorcyclist of mass m was at the point A, and this motorcyclist has initial velocity is u, which is in horizontal direction. Height of the point is h. Height of the point A at which the motorcyclist exists is h, and motorcyclist rolls down along AB and reaches to the point B, and at the point B the motorcyclist has the tangential velocity v2, which is root over 5gr, and this motorcyclist will go round in the globe successfully, provided the tangential velocity is v2 equal to root over 5gr. Using the principle of conservation of energy between the 2 points A and B, we get half m u square plus mg equal half m v2 square plus mg into 0. So finally we get h equal 5 by 2r. H equal 5 by 2r, which is the maximum height from which a motorcyclist in a globe of death must start in order to go round a globe successfully. Maximum height from which a motorcyclist in a globe of death must start in order to go round a globe successfully.